Um, so yeah, this talk's going to be on data-driven decision making. So for most of today, I feel like we've heard about applications where uh, like that aren't sequential. Applications where it's like you'll do one thing and you'll try to pick the best thing to do in that environment. Like you'll make the best object detection, or you'll make the best classification, or something like this. And that's it. The There's this whole other side of AI where it's the actions you make influence your environment. And if you can model how they influence your environment, you can like think about what you can do to get you what you want in that environment. So that's kind of going to be the area of this today. So like probably some of you guys like know reinforcement learning. I'll be giving more of like high level overview of planning, which is of reinforcement learning is just one piece and one, I guess, tool. I guess I'll talk about where RL kind of fits into this, but I'll be mostly focused on like how you can solve decision-making problems without reinforcement learning, like without having to rely on a simulator or millions of like training steps or something like this. Great, yeah, and I guess so my background is I'm doing my PhD at Stanford in robotics. I just taught the follow-on class I taught the advanced sequential decision-making class, or head TA'd the advanced sequential decision-making class this last term. And yeah, my research is in data-driven decision-making with applications to autonomous driving and to energy systems. So it's cool that like you can use the same tool sets for both. Like you can use the same things for decisions in autonomous cars and the same things for decisions around like smart grids, or like discharging and charging batteries and stuff like this. So, and then this is more of kind of like a high-level overview of planning. So I won't really talk about like my own research. I'll talk more about giving an overview of planning and kind of like how to model systems where you can understand like how the actions you take affect your environment. And then I'll give one algorithm for solving these things in different regimes, and then I'll give an example, like a pretty recent example where these things are used successfully in systems today. And I think most of this material comes out of the Stanford class on decision making. For reference to its like popularity, I think NLP had around like 500 people. Intro AI had 350. Like this last offering, this had around 300. So it's like one of the core like AI classes. And then the book is like freely available online. It just came out this year. It's got like all the code live compile. Algorithmsbook.com. It's like MIT Press. Yeah, it's really cool. Great. So what is like the setting of sequential decision making is when the actions we take influence the future. And the whole point of today, I guess, is that if we can like make a model of how, we can use that model to like plan to our liking. And really, planning is like a core capability of an intelligent agent. And kind of the point of this talk is that there's like a principled mathematical framework for defining rational sequential decision making. And if you can put your problem into this framework, if you have like a sequential problem that you can put into this framework, you can use like existing tools to plan like really well. So this is applied in like all kinds of fields. So robotics and autonomous vehicles might get a lot of hype today. But this is also like things that are very successfully used in energy and finance, healthcare, manufacturing. A lot of the early research for like the math behind this came out of business operations and operations research. And like games, you guys have seen, I'm sure you've seen all the games and like the reinforcement learning simulation applications. And as always, like the money is in advertising, right? So yeah, the point is, you put everything into a framework, you can use kind of existing tools. So really quickly, I want to talk about agency and kind of what the AI model is for agency, or I guess not even the AI model, just a reasonable model for agency. Is that you have an environment, that environment at each time emits observations, and you as an agent have to take actions. And you take actions given your own history of observations and actions. And the point is that your actions influence the environment. So if, for example, you just had some kind of object detection thing, and you detected that there was like a car in the road or something like this, just making that detection doesn't affect the environment itself. It's using that detection to affect how your car might move, which then affects the environment. So again, this is more for like applications where your environment gets affected by the actions that you take. And in order to kind of like help process like how you would plan in such a setting, it's helpful to think of environment states. So states being things that exist on the environment side that aren't necessarily known to you, that maybe might change based on the actions that you take to them. So some examples of states might be like your true robot position if all you had was sensors or something like this. You would take accelerations or steerings or stuff, and your robot would move. But you wouldn't necessarily know the exact position of the robot. You would only be able to sense kind of where it is through the sensors that you have available to you. States that you might know, like this is reasonable to model in this framework as well. You might know the states, and that might be something like a chessboard, where you actually know what the chessboard looks like at all times. Like the observation you get isn't noisy, it's perfect. They might be things that are more abstract, so like whether you are hungry, and the observations you might get out of whether you are hungry might be like if your stomach's rumbling or something like that. So it's like maybe you don't have a really great like measurement of your hungriness or something like this, but you get kind of observations that are tied to that, and you can use those observations to guess what your internal state is, and then you can use that guess to plan about whether you should eat or not. Or like maybe something that's like not dependent on you at all, like how much your partner likes you right now or something like this, based on kind of like the reactions you're getting out of them. And hopefully you want to plan to make your partner like you. Maybe you don't. I don't know. Who knows? But your point is that you have to kind of like make these actions just with some understanding of what's happening in the environment without necessarily knowing exactly. So the rational part comes in when you actually want to like figure out how you would act relative to this like system. And the point is that like reward, like the thing that is good to do, like the thing that is like defines how you should plan, is that something that's defined, I'll say in this system, from the agent. So the agent would define like a reward function that would say, for example, like +1 for getting to a target in this like robot example or something like that, or +1 for winning a game of chess, or -1 for being hungry and not eating, and -1,000 if your partner hates you or something like right now or something like this. Or I don't know, if you're sadistic, maybe you define your reward function as like +1,000 if your partner hates you or something like this, right? But the point is that it's like something that you define, and it's given you define it, you can like use existing frameworks to come out with policies that are rational and optimal towards that reward function. So the kind of mathematical framework that like encompasses all of this, it's called the partially observable Markov decision process. And we talked about kind of like the principal like underlying components, states, actions, and observations. But there are other like really important pieces. So I'll put this in terms of an example where you have to figure out how to optimally feed a baby while only telling whether or not it's crying and having to guess whether or not it's hungry. In that case, states would be like, the true thing that you don't know, whether or not the baby is hungry. Actions would be to feed it or not to feed it. Observations that you would get would be whether or not the baby is crying or not crying. And these are observations that would be like tied to the state itself. Like there would be some probability function, some observation model that would say the probability that the baby is crying, given that you didn't feed it at the last step and that it's hungry, is like 0.9, something like this, like a probabilistic model to like quantify this. And like the really, really, really important piece that is like the essential piece for kind of all interactions with an environment is like the transition model. So what will happen to the baby at the next step if you feed it and it's not crying, if you feed it and then it's crying, whatever, like, and what are the probabilities of doing so? So kind of where like, I'll talk about where data comes in, but it really comes into like learning this transition model. It comes into like figuring out how your environment will evolve given actions. So given all of this, you can define an agent policy as one that maximizes the expected future cumulative reward. So that doesn't mean it maximizes what it should do right now. It maximizes what it should do to drive the system such that over all time, it gets the best possible chain of rewards that it could get. So if that means taking something worse now so it could do something better later, if that overall is better, that's like what a rational agent would do. So for example, in chess, like, I don't know, or games, it might be part of good strategies to take actions that might seem suboptimal or seem, like weird to do now so that you could drive the system to better states later. And, we've seen this with like AlphaZero doing this. This is like equally true that for other systems that use these, that you get policies that wouldn't necessarily be obvious to like a human who's trying to do the same thing, but are optimal relative to like the other pieces of the model. And so it's useful to kind of think about this in terms of like utility of being in a state. There's the best possible utility of being in a state, U, as maximizing over all possible policies that one could take over future rewards from that, starting from that state. So I'll kind of give, like, just to showcase what this, like, an example of planning with a POMDP would look like. You could consider planning in this noisy environment where this like robot who is highlighted here doesn't actually know where it is. So even though it's highlighted, internally it has no clue where it is in this environment. And it has to get to this kind of like green goal while avoiding this red goal. These like blue things that are being shown are kind of like ideas, like internal ideas that it has of where it could be. And you can see kind of like as it interacts with this environment, it gets better and better information of where it could be until it feels like it has enough information to a point where it could just navigate to this goal. So I think it just hit the second wall and the belief collapsed. It just hit this third wall, and as it just hit this third wall, that like blue collapsed so small that it's like, pretty sure where it is, that it could just go to the end. But like while it's just starting out, like in those first few steps, it could have been anywhere. Here it knows it has to be like on a wall somewhere, but that wall could be anywhere. Once it hits that second wall, it's kind of like figured out, the walls that it might be at. And then kind of once it hits that third wall, it knows that, okay, like I'm definitely in this area. I can just go towards the end. And like what I really, really want to emphasize with this is that unlike the reinforcement learning like applications where you'll see, like none of this is learned. So like none of this is done in a simulator until it finds a good policy. You can just feed it your models like instantly, and it'll come out with this like best thing to do given those models, which is like awesome for engineering applications where you can't just like trial and error things with an environment until you have some understanding of that environment or something like this. It's like you just feed it in the model and it'll give you like the best thing to do. I think that's like a really important distinction to make. For the rest of this talk, I'm going to focus on like planning applications for the fully observable setting, just because it makes it easier to talk about algorithms and stuff like this. A lot of times you can just combine using methods to take your best guess at what's happening internally, like where the state is, combine those with planning from like fully observable planning from that best state to get really, really good policies. That's not like, you don't have to do that. You can also plan within this framework. There are like algorithms to plan within this framework. That's kind of like the direction my research is going. And for those applications, there's kind of been a lot in like the last 10 years as well. And especially in terms of like larger and larger state spaces, larger and larger observation spaces. But just to talk about these things, I think it'll help to talk about when you know where your state is, when you know where you are at all times. And then the important part to this conference is like the data-driven part, right? That's like kind of where everyone really cares about here. Where does data actually come into this? And it might seem like small, it's not easy, but the actual data coming into this framework is like how you go about learning your transition model. So how you go about understanding how your system will like react to different actions that you might take in it. And given you've collected a lot of data, you can use that data to create like an approximate transition model. And kind of the point of this talk is that you can use that approximate transition model to plan really, really well. Cool. And to kind of highlight a big difference between what I would say like planning and reinforcement learning is that, at least in this setting, you're assuming at least part of the model is known. So specifically, the reward functions are known. That makes sense for probably most things that people who just like want to pick up reinforcement learning and just use it would use it for. Because really, it's like when you're the one who's defining the reward, when it's not something that's given to you from a simulator, it doesn't really make sense to try to learn that reward function in a simulator. It does make sense to put that reward function in a simulator and like try to reverse learn that reward function. It just makes more sense to just try to learn your transition dynamics and use it like with existing methods to plan. And like for more people who know about this, so this kind of setting is also similar to model-based reinforcement learning. In model-based reinforcement learning, you want to separately learn transition dynamics and reward functions, and then use exact planning methods to plan. So this will be on those exact planning methods. Okay, yeah. Let me pause here. Let's like just take some questions on setup. This might be too like high level, like as in it might be too obvious to people who, like from their intro AI class or something, or maybe not. So yeah, maybe we'll pause here for questions and then can go into different settings and algorithms and applications and stuff.
I guess I'll start by a question. So in this particular case, we have continuous rewards, continuous actions, and continuous state. We can have.
Can, either or, yeah.
However, how does that tie in with having a differentiable model that we're learning for the transition model?
Yeah, so the third setting I'll talk about really amenable to differentiable models. And it's probably like what you want to do with differentiable models. So
in here we don't have anything differentiable.
In here, I'm assuming it's not useful to have anything differentiable for the first two at least. Like you could or you couldn't, but the point is it maybe doesn't matter.
And by saying exact policies, can you a bit expand what do you mean by an exact policy, like greedy or something like that?
No, so yeah, so exact meaning like it's as close to optimal as you can get given the method and your reward function. So greedy, so for reinforcement learning, a greedy policy would be you're trying to learn some estimate of your future reward from interacting with your environment, and then given that estimate, you take the best thing given that estimate or something like this. This is saying like this is not doing that. This is like this is the best thing. Because the point of why you would do greedy or like epsilon greedy in reinforcement in like Q-learning specifically would be that you're not actually trading off exploration with exploitation. The point of these is that these have handled all kinds of like, you don't like the point of handling exploration versus exploitation in reinforcement learning would be to get better and better understandings of your environment. The point here is that you have a good understanding of your environment.
Oh, so that's what you mean by saying we have like a transition model that's already given.
Yeah, okay. And it can be learned, but like the point is that you have that model.
Okay.
Yeah.
And when you say that the reward function in this case is given by the user, isn't it the same as or?
Yeah. So the second, I'll talk about AlphaZero. That's the second application. I feel like people think about AlphaZero as reinforcement learning, and it's really more supervised learning plus planning. Yeah. Cool. Has anyone been thinking about like a problem, like a sequential decision-making problem that we can quickly try to formulate as a POM-DP? Just throw out like any decision-making problem.
Someone asked me if we can replace the government with. That's a hard example.
No, I feel like, I mean, abstractly. Yeah. So abstractly, to do something like this, you might define your reward function as like the final state of your country or whatever that is, or a reward function based on the state of your country having these good qualities. And then you might want to think about, you might have some model of if I change this or if I change this, how will it immediately impact the state of my country? That would be your transition model. And you would want to figure out to do things in like a correct ordering, like how to plan around this correct ordering in order to get this like best reward over time, right? It might not be good to change one particular thing now when you can do it better later for cheaper and extract higher costs now from doing other things right now, or higher reward now for doing other things right now. The observation function would be like, maybe you don't know the exact state of your country, but you can tell by like, explosions in malls or something like this that, that these are noisy observations of like the state of something. That wasn't a good example. Sorry?
We don't have the reward function as well.
So you would define it. So you would define a reward function based on the state of your country. So yeah. But this is why it like makes more sense when you can. These are hard things to do abstractly for something like this, right? But when you can collect data, it makes a lot of those things easier.
So if we feed enough data to the model, will it create assumptions
Yeah, so for the transition model specific, so reward function, you can just define how you want that to define. For transition model, yeah, if you feed it enough data, and in that data it's interacting enough with the environment, then you would expect it to be able to do this. And it also often helps to use expert knowledge in your transition function. So part of it based on expert knowledge on how you think it might behave, and then part of it maybe based on data. And that's kind of like how you as a human might plan. Like you don't obviously know how your actions are going to interact with the environment, right? But you have some kind of like rough internal model of a guess. And even just like even just rolling out that guess to make actions or something is better than just fully not planning, right? It's better than just doing whatever better than just acting immediately with no kind of prediction of how your actions might affect the future. Does that make sense? Yeah. Cool. Great. So I think with that, I'll talk about 3 settings. So the first setting is for offline planning. So what that means is that given these models, before you interact with your environment at all, you can just come out with a good policy that works from every state. You can think of this as like a lookup table where from each state you map to the best action. So an example of this would be this kind of like grid environment below. You guys maybe know this from your intro AI classes, but like a grid environment below where when you move, you transition stochastically. You don't necessarily go to the state that you want it to go to. And some of these states have like good rewards and some of them have bad costs. So in this example, this like bottom right state, you get high reward. This left or this red state, you get low reward or bad cost or something. And I think there's one here that you get medium or something like this. And an offline planning algorithm would just, before you interacted with your system, would just like learn the best policy. And so it would basically learn, and it would do this using dynamic programming and keeping track of the expected future reward in every state. I'll briefly say that in the next slide. But the idea is that these kind of shades of blue highlight the expected reward you expect to see from just being in that state and taking your best policy over all time. So there's kind of like medium utility states and like high utility states close to these reward things. But then the actual policy, avoids this red thing or whatever. This is just to kind of highlight what an offline planning algorithm would do. And pro is that you can analyze and test the stationary policy. Con is that these might be typically limited in the size by this, like the exact algorithms would be limited by the size of the state space. They're approximate algorithms as well. So I'll briefly talk about these. The one way you would solve this exactly is by iteratively applying Bellman updates. So this goes back to like 1950. So this is not new. So what you would do is you would start with, say, values of like 0 in every state or something like this at your first iteration. And then you would just iteratively apply this equation that says the value at a state corresponds with the action that maximizes immediate reward. It's this immediate reward function, plus discounted expected future reward. So what that means is that my utility, like here, would be the sum of the reward I would get here plus pick over all the actions I could take, and go based on the probability of transitioning to next state given that action and the utility of that next state. So the point is that, like, yeah, that you could just apply this iteratively and just have this will just converge. So in this first step, you start with zeros everywhere. By like the first iteration, you can see you've propagated like the immediate rewards, and you propagated these back a little bit to other states. By like the third iteration, you've propagated these more and more and more, and after like 7 iterations, this thing like converges. So this is like probably covered in most intro AI classes. I'm sure you guys know this. Really cool aside for the Armenians in the room is that you can write solving an MDP as a linear program, and linear programs were proven to be solvable in polynomial time by Leonid Khachiyan. So there's this really cool article, or front page picture, I should say, the New York Times. And you have over here, let's see, this is 1979. So you have Iran's civil government out, hostages face death threats, oil exports believed halted in the upper right. And then you have a Soviet discovery rocks the world of mathematics. And it just like outlines that how impactful this proof will be. And it's like before people really understood how impactful the proof would be. So this is kind of like one of the areas where that proof is impactful. So that's sick. Yeah, so I don't know the last time a proof was on the front page of the New York Times, but hopefully Yerevan and keeps at it. This will be happening soon again. So yeah, that's like a little brief aside that people might find cool. So for continuous spaces and for like larger state spaces, you can rely on kind of like an approximate version of that last algorithm. So there's kind of like 2 ways you can do this, and this is probably more applicable to the data-driven decision-making people here, because a lot of time, I guess, if you want to, for data-driven decision-making stuff, it might be more likely that the space you want to make decisions is some like latent space, and that latent space is continuous or something like this. So how do you define value in this continuous space? So kind of 2 different ways of doing so. One might be local approximation, in which you just pick a set of points that cover that space, and then just track the value at those points, basically, and then use some kind of like, I don't know, distance thing or something like this to estimate the value in between those points, and you can basically apply just the last algorithm and do the same thing. The other method be global approximation, and then you would just fit a function, you would just fit a neural network or something like this to do this for you. And yeah, so the point is that you can extend this thing to higher state spaces where you might not be able to do that exactly. I've kind of left out the math because it's like the last talk of the day. So if you want to know more about this, you just look into that book or something like this. And I kind of wanted to bring up an example that does this in real life. So if you took a plane to get here, which I'm assuming maybe some people did, then that plane since 2018 has been equipped with a system that alerts pilots with instructions to avoid impending collisions. And that system is using this. It's using approximate value iteration. It says, given states like relative position, speed, orientation, pilot response times, or something like this, issue alerts whether to climb or descend in case of an impending collision. So in case of another plane in the airspace. It uses transitions that are partially known, like aircraft dynamics, along with maybe some learned models for pilot response. And you would extract, it defines like a reward function based on kind of what the designers wanted. So large penalty for collisions, medium near miss penalty, a penalty for reversing your decision. So if you have to give a pilot an alert to climb and then go back 5 seconds later and tell it to descend or something like this, that's like also bad, that's like dangerous. Punish that accordingly. And you can solve this exactly like ahead of time, analyze this, have a policy that just comes out and a policy that just works the same from every time the 2 planes end up in the same state. So this policy might look like This is a cut of that policy. So it's 7-dimensional state space. So this is just 2 dimensions of it. In this thing, it's the intruder is level with you. You're not climbing or descending. There's some time to potential collision on the x-axis and relative altitude on the y-axis. And this one's kind of obvious, right? This is like if you're above it, you should climb to get higher above it. If you're within some envelope, if you're below it, you should descend. Maybe if there's still like a while to go before you get really close, you should wait a bit so you don't have to unnecessarily tell it to climb or something like this. And then there's kind of this like really interesting behavior where if you're in this like weird red envelope, you actually wait a bit till you know more because you don't want to tell it to descend and then have to tell it to climb. So the point is that these is like the exact right thing to do given the reward function and transitions and whatever that were defined. This is like another example on the right. If this example, I think the plane is coming from below the intruder. So if it's still sufficiently below the intruder, it should descend. If it's getting at least close to level with it, it should climb or something like this. So yeah. Great, so that was offline planning. A big kind of hurdle for offline planning is that it requires you to build a plan from every state, and it could be that your state space is like massive. So in online planning, you, while interacting with the environment, build a plan that just goes from the current state that you're in. So this reduces kind of like what you would have to search over or something like this, or the situations that you would have to think about. And then this is typically coupled with what's called like receding horizon control. So the idea is to plan multiple steps ahead. So maybe you make a plan that's like for 10 seconds or 5 years or something like this. Execute the first part of that plan, see how that state actually evolved, and then do some replanning. So this makes probably a lot of sense for how you guys interact and how we all interact with the system, right? We don't consider doing everything all the time. We just consider going from where we are right now, doing the first thing we can do, and then replanning, right? And this is like how you would do most physical things as well. So like cart pull swing up, if you've seen like reinforcement learning things where it just like tries to learn a policy that swings up, sorry, this isn't cart pull, this is like double pendulum or something, where it tries to swing up 2 pendulums from ground. It just tries to like simulate this 1,000,000 times to find a good policy that does it. In real life, you would just not do that. You would just plan, you would just use the dynamics that you know and just like plan and get an action thing and then replan and do this. This is what you would do for like robotics and stuff like this. And then this is kind of being shown here. So the blue line is it's like expected plan, and then it just takes the first action. So sorry, not the blue line, the dotted line, which is hard to see, but it's like extended over here, and it'll just take the first action and then replan if it has to or something like this. So one algorithm for doing so, sorry, let me drink some water really quickly. One algorithm for doing so usually for discrete states and actions, but it can be extended to continuous as well. Really popular algorithm for doing so is called Monte Carlo tree search. I'd say like the current version, like the popular version of it is maybe like 15 years old or something. Newer version, there are other things, whatever. I'll go into this. The naive thing that you would think to do in a setting like this is to just search, right? So you would take an action, see how your system evolves, see the possible states you can end in, because remember that state transition is random, or it could be. And then you would plan from each of those options, and then you would build this kind of like search tree, right? That's kind of like the naive thing to do. But if you want to go like 10 steps ahead, right, then you have to plan the number of states times the number of actions to the 10 branches of that tree, right? So this like does not scale really, really well. The idea of Monte Carlo tree search is to sample the search in that tree along areas that you think might be good. The way you do that is by trading off kind of your estimate of how good an action is with some kind of like optimistic exploration bonus that says, maybe if I haven't explored this action so much yet, I shouldn't trust my estimate of that action right now. I should maybe explore more. So you would sequentially like shoot some different things down this tree, and then figure out what kind of like estimated expected rewards you get at the leaves, and then propagate this information backwards. And what's like really interesting, there are a few things that are really cool about this. One thing is that what do you kind of use at the bottom? So once you get to a leaf, how do you estimate the expected future reward you'd get from that leaf? You could just roll out any kind of policy you want. You can also roll out like an expert policy. So you can take like either something you've used approximately with the other methods that we talked about, or an actual expert. So like someone who's been interacting with the system for like 30 years, have them write with you in like code what they would do, and just use that as a policy like at these leaves. And the actual policy that you would get by searching and using their policy at the leaves would be like better. And yeah, so that's like cool. To give a little note about Monte Carlo tree search, it requires being able to generate samples, though, of next state and reward from state and action. So it is like inherently planning. It's like you need to know how your system would evolve given taking some state and some action or something like this. So an example would be like you would have to pre-program the chess transitions or something like that into a system like this. That's why it's like not necessarily model-free reinforcement learning or something like this. It requires knowing how you would transition given some action. And what AlphaZero does is literally that, like literally Monte Carlo tree search with just like 2 extra like steps that, I don't know, maybe they weren't obvious 15 years ago, but they seem like really, really obvious now. Those 2 extra steps would be, one, like I said, you could estimate values at the leaf nodes with some expert policy. They just estimate it with something that they've regressed. So they looked at actual, given a board, who won, made a function that regressed, given all their data, given a picture of a board, who won, and used that to estimate probability of winning at the leaves. That's one thing. And then the other thing they did is that you can kind of bias what actions you sample. So if you don't have to choose actions randomly at each of those things in your sampling. They biased it towards basically previous searches. So in doing previous searches, you get maybe over 800 simulations or something. You get some kind of distribution of what actions it thought were better and better. And it just basically made a regression. It just regressed to this like more informative thing, and then used this to bias how it does its search. So it's like with these 2 kind of like really, I don't want to say simple, because again, probably wasn't obvious 15 years ago or something, or 10 years ago. But with these 2 things, you get like state of the art for board games. But I should say again that it's like really important to understand that these, like AlphaZero pre-programs the game transitions. Like it pre-programs knowledge of what's a winning board, what's, if I move my knights, like what does the next board look like, right? If you don't know this transition function, more recent thing, mu0, which you guys also might know about, just learns it. So this is definitely more on the like reinforcement learning side. Like if you don't know this, maybe you just learn it in the latent space. And then you just plan with Monte Carlo tree search in the latent space. But you're still learning the transition function and using that transition function that you've learned to plan. And so yeah, this is like, this is also, so this achieves state of the art in games. And so what's really, really cool is that it does it both for board games and Atari simultaneously. So it just kills for Atari, it just like kills the model-free reinforcement learning things, which is awesome because it means it makes sense even for those games which are usually like pretty reactive. It makes sense to consider like a multi-step future plan. Also, I should say though, so even though it does achieve state of the art in like chess and these board games, doing so simultaneously, it's playing against, I think, the state of the art thing. So it's still like, it would still be better to use transitions if you had transitions rather than try to learn them in latent space. This year, it's kind of like the first real life application to mu0, so like leaving games. So DeepMind used kind of the same algorithm for video compression. So they basically have this kind of like encoding system where at each frame you can choose like an encoding parameter that says how much you should encode like that frame of the video, and it's important what sequence you choose those parameters in. And then they basically made a thing where they made a reward that basically encouraged it to do better against its previous self and hit basically similar quality while lowering kind of the compression rates, increasing the compression rates, whatever, getting better compression rates. And yeah, they achieved like 4% bitrate reduction live on YouTube, which is a huge deal because these like encoders have been billions of man hours have gone into like basically optimizing all the parameters of these like codecs and stuff like this. So you can even take these kinds of like fixed things, put them into like this kind of framework and get better policies.
How do you work on the quality?
Yeah, so they, in their thing, theirs was in like a constrained reinforcement learning setup. So they basically had part of their reward functions like trading this off, and they baked this into their system. So that's kind of like a big part of that paper is how, yeah. But yeah. Okay. Great. So that was the second part. Yeah, maybe this is a good time to pause for questions before I go to the third kind of like regime of stuff.
For the last one, for this YouTube thing, I didn't know that this mu zero line of research achieved anything serious.
Well,
Nice to see. So,
the thing, I guess one reason it's hard is that it's like really, like at least for other things, like for language models and stuff like this, it's like not easy, but like other people can go train their own, right? For this, it's like one, they use some special things on Monte Carlo tree search between like like hybridizing a lot of things and like there are like a lot of tricks that went into kind of like the engineering aspects of how you do this on like a large enough scale where you can take like millions of transitions and stuff like this. So that's one thing that's not open source, obviously, which sucks. And then ridiculous compute. But I guess it's maybe wasn't as important for others because mostly these like reinforcement learning specifically has been only great for games. Because when you get to like stuff for real life, like you have to deal with the difference between training this thing in a simulator for that thing versus real life.
what was the simulator equivalent here? Like,
Yeah, so they just took
an algorithm itself?
Yeah, so they just took real yeah, exactly. They just took real videos and how the compression out. So there was some baseline like open source. So yeah, there's the codec, and then there's like a baseline open source thing for choosing parameters of that codec, and then they're basically comparing against this choosing parameters of that. Yeah.
And when you say reduced amount of compute, it means like lots of videos, lots of parameter versions before it discovers the quality.
I'm not entirely. So I think it's more that you need to be able to make. So like for example, each time you do, so you're doing one of the, here. Let me back up a bit. So you're doing one of these searches at every step of your simulation, which is different from just model-free reinforcement learning, where you're just taking a screenshot or maybe some memory or something and just taking an action or something like this. In contrast, here at basically every single state, you have to shoot kind of like 800 simulations and see how your system would evolve given those simulations or something like this. And then you have to do this for each, say, like game, for each chessboard across like a game, across like 1 million games or something like this. So I think the original AlphaZero is like, what, days? I don't know, like 12 days or something like this. I don't know, long time. I don't know, I could be wrong, maybe not. These were like, I think they definitely have like a lot of hacks that they haven't released to be able to like do things with this. And I think hardware, there's still a lot of room for hardware for like this particular aspect. Like it hasn't been focused in this particular region. Because I think because people mostly looked at like this is like a cool thing to do for games and not something you could do for, like other things.
A question regarding Monte Carlo tree search. As in any like heuristic based sampling, stochastic sampling, you're bound to get leads that lead you to a local minima of the problem. And are there like any guarantees or like pseudo guarantees or like approximations towards like if you're to have this amount of compute used or this amount of samples taken from the tree, then you're bound to get towards like the nth percentile of the ideal expert solution.
Yeah, I'm sure. Yeah, that definitely. Well, so for sure, if you take infinite samples, it will converge 100%. Like that's like like proven. Like I'm not just talking. I'm sure there's things where number of samples and like it's based on upper confidence trees. It's based on like UCB search. So it's saying that as you take more and more samples of somewhere that you didn't know about it, your upper confidence bound would shrink and your planes would come out and you would basically it's based on all the math for UCB search. Yeah, cool. But yeah, but the point is like it really does depend on how good your estimates at the leaves are, and if you can do better by estimating what the value at the leaves are, you can do better upstream. Otherwise, it will take longer to get better and better estimates at the leaves.
Because for players like alphabet search and like other heuristic algorithms like that, depending on the domain and some metric on how hard the domain is, there are some guarantees of getting it. I was wondering if there's something like that for Monte Carlo tree search.
Yeah, it's not personally my domain, but I'm very confident that there are. So I'll put it like 90. It's like a lot of people are working on this. Like it's yeah. Great. Okay. So the very last thing, I'll try to cover this in the last minute, is like online planning with determinized transitions. And this gets into the question you asked earlier about like your dynamics being differentiable. So what you can do is say like if your thing's not stochastic, or you can approximate your stochastic function is not stochastic. So instead of taking a mean and uncertainty around kind of states you might end up in, just take the mean and then plan around means. And this is great. Like this just like one, it reduces all of the branching over searches. Like if you were still going to do a search, it would reduce all of the branching over searches, right? Or sorry, over states. I meant search. Over states. But then if the important part that you're saying is like if your actual transition is like just differentiable, then the resulting optimization problem gets like really easy to solve. So like this is the resulting optimization problem regardless, right? You don't have to do the search over branches or anything like that. It just turns into this. And then the question becomes, how do you optimize a set of like 10 actions given knowledge of your transition function? And the ways to do this is like really any method you want. So like you can, gradient descent actually works like pretty well for these. And what's cool is that since you have one objective, you can kind of start your gradient descent in batch from like 1,000 places and just take the one that's best, because the action sequence that's best and gives you lowest reward is like the best one under your reward function. It's not like, great. So this is called open loop planning. So previously, everything else has been closed loop. So closed loop means it assumes in your plan that you will take the best action at all future states that you might end up in the plan. Whereas open loop means you just have a one kind of like set of sequence of actions that you're going to take. It can be suboptimal if your noise is multimodal. So here's an example of on the right of like when that would be the case. So in closed loop planning, in this example, you get reward after your second state. You can go up or down at each thing, but if you go up in the first step, there's like a 50-50 transition. So in closed loop planning, the value of being in state 1 is 30, because regardless of whether if you go up here, regardless of whether you end up in this state or this state, you know that you can take the action that would get you to the 30 reward and avoid the 0 reward. In open loop planning, that's not the case, right? In open loop planning, you have to choose between down, 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 up, down, up. And if you choose up anything, the expectation is 15. So you would choose down something. So that is to say it can be like suboptimal, but since it's just so much easier to optimize, it's just like probably what's used for like most things that are in continuous spaces. So I'll give an example that for vehicle control. So this is probably used on like most modern like vehicles. So like autonomous cars, SpaceX figuring out how to like move their fins and their like pulse engines, whatever, to land their rockets or something. It's like uses this. So the idea is to build a reward function that does something smart. So you might trade off between targeting a final state, so getting your position getting your rocket to the ground or something like this, punishing unnecessary actions, so maybe without making too much thrust or something. You can add on things like making your actions like be smooth or something like that. You can add on kind of whatever you want into your reward function to give you the behavior you want. You would use your dynamics, which in the case of rockets or vehicles would just be the physics. And since you're just doing some optimization problem, you can easily add on, well, I won't say easily, but you can add on like other constraints, which also make this nice. Like you can also add on to like avoid collisions. And so like for driving, this avoid collisions thing would be fully data driven. Like you would basically take a look at all the cars around you, use some model to like predict how those cars, what they're going to do the next time steps, and then add these as additional constraints to drive while avoiding their trajectories or something like this. And then you can solve this through like sequential convex programming usually, like really fast. So yeah, in this problem, like the problem here I mentioned, the dynamics were like they're physics. They just come from physics. Other problems, you can learn the dynamics. You can learn to predict safety constraints. Okay, yeah, I said that for this. Another example where they just learned the dynamics was like from this paper where they basically like took this kind of like neural network, like they just learned a neural network dynamics function, basically. So they took some controller that they knew was like okay, put it on a car that's just like racing around a track, learned kind of how the car transitioned a little differently from the physics that they thought given, say, like hard road conditions or something like this, and then use that model to plan optimally relative to the reward function and basically, I don't know, set some racing records or something like this. And the point is that though, once you kind of like have it in this, you can use whatever optimization method that makes sense for your problem, be it like gradient descent or something like this. This one uses like MPP, like model predictive path integral or something like this, and just solve your system. And then this is what's used for like portfolio allocation, for like energy, for driving energy systems. You would just take kind of like the most likely dynamics and plan with some optimization method around those dynamics. Yeah, because it would make more, because energy grid stuff would probably be in continuous spaces. You can build models forecasting renewables, forecasting, I don't know, weather, things like this. You have some model of given you take these kind of charging decisions or these kind of like charging, uncharging, battery, whatever, how the system would evolve. And then you would just optimize like how much to charge or discharge or how much to turn on this, or if to turn on this or to turn that off or something like this. And you could do so with this kind of like optimization setup. So this is the last slide. This is kind of like, this is a really, really cool idea. People have like kind of been using these for more and more applications. I think like we'll see more research papers where they use this to like more things. So in the last kind of section, I talked about like determinizing transitions as taking the most likely transition. Like if you have this kind of like Gaussian or something, you just take the mean as the exact transition function. If you have this kind of like really noisy estimate of dynamics, like you have a lot of uncertainty that might come from different places, you can do kind of like a reparametrization trick thing. Like you can basically like sample some scenarios, like fix some noise ahead of time to sample some maybe like 5 different scenarios of things that could happen, given if I knew actions, these things would evolve this way. And since you only care about the first action, you can solve these kind of like optimization problems in parallel while constraining the first actions to be identical. And that way you get kind of closed loop behavior while taking into account like different modes of uncertainty. If you have like, if your uncertainty is like all over the place. Cool, that was the last thing. So to summarize, you can model uncertain environments with partially observable Markov decision processes. And in doing so, there's just a lot of tools that exist to just solve them. If you learn a rough transition model from data, you can make good plans. This being better than just trying to like have some reactive thing where you just take a look where you are now and make a decision. You can use kind of like your dynamics, your transition model to feed through and see how different actions would affect your future. You can learn offline policies in large state spaces through approximate value iteration. You can plan online closed loop through Monte Carlo tree search. You can determinize transitions and plan open loop quickly online. And to give some additional resources, so this POMDP's JL toolbox just has a bunch of the recent POMDP solvers already implemented. So you can go and just define your problem as like a POMDP and just play around with like, just use this to solve it optimally or whatever, both online, offline. That's for closed loop. For open loop, just these are, I guess, some different, like the first three are just like common optimization toolboxes. The fourth is from the last paper I mentioned, the model predictive path integral. And yeah, and then I guess for books, so this like, yeah, I give kind of a lot of, yeah, like concepts that are maybe harder. This Algorithms for Decision-Making book starts by building everything like from scratch, like from zero, and then kind of gets to this. And then it also handles more reinforcement learning, it handles like multi-agent stuff as well, like games, things like this, and also handles more on the actual POMDP planning. For most of this talk, I was talking about planning fully observable, like MDP planning. Great. I think that's right on time. Maybe like a time for a question or something. Sure.
What model is more appropriate and relevant? For example, in healthcare, we have, for example, when doing aging, we have for rejuvenation of the organs, we have to have exact and very timely intervention with very stochastic environment. We have very multifactorial stochastic factors. For example, hallmarks. What method of algorithm is more appropriate for prediction of all these stochastic transitions?
Yeah. So yeah. I think if the actions are like discrete, which I think they often are for health things, like do I intercede? Do I take this kind of like health action? Do I even do things to gather more information, do more diagnostics, like things like this? I think for those discrete action things, I think those online planning, Monte Carlo tree search things like make sense. But it is, again, still really dependent on like, can I first even build a model that says how likely am I given like a health action to actually see an improvement for it? There are a lot of people that are like kind of using this in that field though, and these kind of like optimal decision making things like in that field. Like I could probably point you to some more specific things. We were talking about with Michael Gear yesterday about like if you could build a model. Oh, I don't know. Maybe if you can build like good models for like reactive health too, based on like suggestions that you can give or something like this, like maybe you would be able to, plan with those things, right? Yeah. I don't know if that was a non-answer, but.
One question is, can you use anything like message passing or expectation propagation frameworks in order to model some of the transitions or maybe the state space itself, like instead of doing Monte Carlo tree search sampling?
Yeah, I want to say yes. So like message passing through time, like yeah, I want to say I feel like I've seen things like that. Yeah, I can look it up really quickly. I think I've seen things. So I guess my one qualm I've had with it's not a qualm. Like for example, we've seen like multimodal models that do decision making things pretty recently. One qualm is that like they don't really do planning. Like they take kind of demonstrations and then they try to mimic these demonstrations or something like this, right? Whatever system you use, to fit within this model, I would say it would just need to also propagate like rewards and stuff too, right? Which those don't, but that's not really your question. But yeah.
No, I wanted to know if like instead of taking the mean of like a continuous state space, basically discretizing it in a way, we can do some kind of like message passing to mimic the transition actually happen, and then actually do like everything we talked about.
So you mean instead of like, okay, so you're saying further approximate an approximate transition function.
Because it's faster.
Yeah, you could, yeah, for sure. Yeah, you can definitely further approximate transition. Yeah.
I was interested if there's like a line of research that covers that. If that's worse, considerably maybe better.
I'm sure it depends. I can try to. Yeah.
Any other questions?
Cool.